To kick this off, I'm actually wearing two hats today. I'm going to give the first presentation and update you on what's been up to in Singapore. So NSCC Singapore is a national infrastructure for research funded by the National Research Foundation. Our vision is to become the Singapore go-to partner for accelerating transformative research using HPC technologies. This anchored on three strategic pillars, as you can see there. Enhancing capacity and diversity, which is to ensure adequate, relevant, and dynamic infrastructure are provisioned to power research across all domains. Operational excellence, which to us is to use automation, intelligent tools, and leverage global network of collaboration to ensure reliable, responsible services to our users. Last but not the least is talent and user enablement. We are committed to nurture the talent pipeline for HPC in Singapore, and also enable our users to max out the resources that they're given to and improve the efficiency. Being a national research infra, we are the computing backbone to support almost all major national investment across research and innovation. NSCC itself is a part of the 37 billion investment by the RIE, which is the Singapore Master Plan for Research, Innovation, and Enterprise. The focus of the next 5 years is to strengthen AI, data, compute capability, and support selected sectoral research. We support top-level national initiatives such as National AI Strategy, AI for Science, AI for Health, and Quantum. Under the National AI Strategy, for example, we serve as the fundamental compute engine for the National Multi-Model LLM program. Our systems are being used to train localized audio language models like Merlion, which are tailored specifically for Singapore and Southeast Asia language setting. On the AI for Healthcare initiative, our compute support high-impact program like Symphony, which stands for Singapore Medical Foundation AI model. And that allows us to scale trusted, domain-specific AI across our entire ecosystem. To make this happen, we've put in place a series of supercomputers in the past decade. We now have a bunch of them in production. The Spire 2A, which is a balanced system coming with AMD CPUs and NVIDIA A100 GPUs, hitting 10 petaflops at the peak. The Aspire 2A Plus, which is a more AI system, coming with 320 H100 GPUs. We also help our users deploy supercomputers on their prem, like Chroma and Prescience, because they need to do sensitive healthcare and medical research. Now we had a new addition to the family, just early this month, called Aspire 2B. It expands our national HPC capacity by 4 times, and it's designed to enable massive integrated AI and HPC workflow over the next 3 to 5 years. We'll also have a 98-qubit quantum system built by Quantinuum, and it's going to be deployed in Singapore towards the end of this year. It's planned that the Aspire 2B will be connected to the quantum system, so we provide a single unified infra for our researcher to explore hybrid quantum classic computing. Here's a closer look at Aspire 2B. It's launched just early this month, June 8th, and it's currently in the pilot phase. It delivers 115 petaflops at the peak, and now ranked 44 in top 500, as announced yesterday. It's built to be a heterogeneous system, support both traditional HPC modeling and simulation workload, which is CPU heavy, but also AI and some of the HPC workloads that can benefit from GPU acceleration as well. It comes with more than 180K Turing CPU cores, the latest generation of Turing cores, and together with 1,500 H200 GPUs from NVIDIA. The nodes are connected to 66 petabytes of high-performance storage, as well as data lake, while the latest Slingshot 400. Our infra empowers a wide spectrum of research domains, spanning all the way from traditional engineering, healthcare, climate weather modeling, all the way to quantum computing, AI, and deep learning. So here is a breakdown of the resource allocation by domains. On the CPU side, traditional computational science still take up the lion's share, led by chemistry, with more than 1/3 of the allocation, followed by earth and environmental science, engineering, and material science. If we turn to the GPU side, it's a totally different story. AI and machine learning dominate our resource allocation, and mostly attributed to the large language models, training, inference. We do foresee a shift in the near future, though, because now we have more and more AI for science projects granted and onboarded. We also have more and more modeling and simulation applications being ported over to leverage the GPU acceleration. So talking about the evolution, in the past year, we start to see a rapid change in user requests and workloads. While massive AI training jobs are still there, people start to ask for more inference service. They can be from domains like AI for science, material discovery, where users now require us to serve common language models or other machine learning models so they can call to inference. Furthermore, we start to see an emerging fully agentic AI workflow, which incorporate AI training, inference, modeling and simulation together with data analysis into one single continuous workflow. The user want to have some automation for originally manual actions and decisions, for example, generating job scripts for modeling and simulation, and with accurate resource sizing. So this fundamentally changed how we manage our infra, our software stack, resource allocation, and security. Users are also vocalizing other needs. For example, there's a strong desire for dedicated resource or reservation, if you like, especially for long-running, large-scale AI workloads. From an operational perspective, that actually creates a constant tension between the availability, guaranteed availability, versus effective utilization of the resource. We're still learning how to support this kind of new trend in an efficient and safe way. We're now working with the user closely to develop a few pilot use cases, such as coding agents, material discovery workflow, and quantum circuits design agentic workflow. We're also rethinking accounting and billing models. For example, from the traditional compute hour-based, moving on to token-based. Another trend we are seeing is more and more domain users with little HPC experience start to come on board due to the availability of the resource. So the traditional way of supporting them through help desk or one-to-one engagement becomes no longer sustainable given the small size of our team. This has driven the idea and vision of what we call HPC Copilot. The aim is to create a proactive AI assistant that can help users, layman users especially, navigate the complex life cycle of running HPC jobs. So at the job submission stage, a user agentic tool to classify the workload and recommend the most efficient configuration. During job execution, it collects and provides user with live performance data and use, for example, anomaly detection to catch any performance gap, inform the user timely so they can take actions against unexpected behavior in their jobs. And when job completed, generate a comprehensive performance report with optimization recommendations. And this data will not be only just useful for the user, we'll collect and use them to inform our future system design and procurement. We've already kicked off a few work packages on individual components of this framework. For instance, we are working closely with Recon on the workload classification using large language models. More recently, we embarked on the configuration recommendation piece of work, and we developed a tool called PerfPredict. So this is an intelligent resource sizing tool that tries to solve the trade-off between runtime and parallel efficiency. Traditionally, users need to do this by themselves. They need to determine the job size either through extensive benchmark-defined sweet spot or through some engineering guess, I would call it. The tool is built to recommend optimal configuration in 3 steps. First, it automatically analyzes the user input data. And of course, we need user consent to do this. They can choose to opt in if they see the benefits. And then we map those input parameters into our historical database for benchmarking. We actually build a regression model out of that. The idea is we can actually predict the performance for each and every job sizes the user may want to choose. And from there, we pick the sweet spot and provide it back to the user as a recommendation. We've already seen some early success, for example, in the VASP application. In the user production test cases, it can achieve more than 3 times speed up from what the user originally picked. The tool is open source, and if you're interested in playing with it or collaborating, feel free to scan the QR code, and that will bring you to the GitHub link. To wrap up, we scale our impact beyond just providing raw computer cycles now. We support our users end-to-end, all the way through resource planning, support, dedicated training, one-to-one consultation, for example. We currently evaluate over 9,000 jobs per day and have enabled more than 600 researchers since 2025. We also build strong communities through community of practices, the annual HPC Users Symposium, as well as Supercomputing Asia, which is a flagship conference in the region. So to end my talk, I wish to let you know that Supercomputing Asia conference will come back to Singapore next March. If I haven't been to the beautiful garden city before in Singapore, or maybe you've been there but missed some great food and people there, please scan the QR code and let us know. I hope to see you all in the tropics. Thank you for the attention.